Alrighty. So you guys should have the previous two examples that I did, and we're going to try and do two more examples here. One of phase transitions, and then the last one will be a heat engine example, and I'll leave it open to questions that you might have. And again, if you have any questions for me, and you have to leave at 11:50, please type that into the chat, and I'll try and answer that as quickly as I can. Or unless you want me to leave it open to questions now. So I'll give you a few moments if you want to ask me questions now while you're here. And I can just do these problems while you're gone. Okay. Not hearing any immediate questions at the moment, but don't let that discourage you. If you do have any questions for me, please type that in the chat, and I'll try and answer that as best I can. All right, so for this example, we can go and look at problem 4 in the book for, I can't remember the chapter, but this should be phase transitions, where it would, transitions, that's right. And this kind of follows the graph that we looked at before. A little bit more here, where we had, what was this? This was the temperature as a function of the heat. And this is for water. And we saw that for the amount of temperature added, in our case, we're going to start at 30 degrees Celsius, and then we're going to have a phase transition here. All right, so there's going to be some latent heat of, what is it, fusion? All right, and then it's going to gain some heat here until it reaches 100 degrees Celsius. And then there's some latent heat of vaporization, and then it's going to continue. Oh, actually, this was minus 20, sorry. Should look a little bit harder at my notes. This should be minus 20, and then it goes all the way up to positive 130. As more heat is added there. Okay, so what we want to do is we want to find the total amount of heat that is needed in order to convert minus 20 degrees Celsius ice with some amount of mass into the equivalent amount of mass, but in this case, it's going to be steam at 130 degrees Celsius. So let me pose that question for you. How much heat is needed to convert 200 grams of ice fully into 100, of ice at minus 20 degrees Celsius, fully into positive 130 degrees Celsius steam. Well, All right, so I'm going to designate certain areas on this graph here. I'll call this Q1, I'll call this Q2, Q3, Q4, and Q5. All right, and here, what we want to ultimately get is Q total, which should be equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. All right, so these are the amount of heat that is required to convert, say, negative 20 degrees Celsius ice into 0 degrees Celsius ice. Q2 would be the amount of heat required to convert 0 degree ice fully into 0 degree water, and then so on and so forth for all of that. All right. You can also have another problem, and I think maybe there were some example problems where, say, you started with a certain amount of ice, and then you're given a total amount of heat that was put into the system, and it might have asked you how much ice is left over, is it fully converted or not, and if it is fully converted, what is the temperature of the water in that final system? So maybe that might be an example too, but like I said, with some of these other problems before, that might be a little bit more work than the amount of effort for, say, a multiple choice question would be. So just be aware that questions like that can be posed in other situations as well. But for us, we're fully converting minus 20 degrees Celsius water into 130 degrees Celsius steam. All right, so let's start. Let's make a note here. Note Q2 and Q4 are phase transitions. And Q1, Q2, or sorry, Q3 and Q5 are temperature changes. All right, so we're going to need both the phase transition equations that relate heat, as well as the relationship of temperature changes for heat as well. So we're going to need Q is equal to the mass times the specific heat times the temperature change, and that the heat for various transitions is going to be the latent heat divided by the mass. Right, hold on. No, it's the, sorry, the mass times the latent heat. So mass times capital L. All right, so we'll start with Q1. Q1 we said was just a temperature change, so we're going to be using this one. So we have mass times the specific heat, and we're going to need the specific heat of ice for that, times the temperature change that we are experiencing. All right, and so for the temperature change that we are looking at, for the mass needs to be converted into kilograms. So 200 grams of mass is equivalent to 0.2 kilograms. The specific heat of ice is 0.50 kilocalories per kilogram times degrees Celsius times the temperature change. And so the temperature change is final minus initial. Final is 0 degrees minus a minus 20 degrees. All right, so that makes that plus plus. And so we get If we calculate this out, I get 2 kilocalories. 2.0, I'll say. All right. Any questions on that? All right. Moving on, we can now look at Q2, which is now a phase transition. And so this will require the latent heat, and this is going to be the latent heat of fusion, because the latent heat of fusion relates to phase transitions between solids and liquids. All right, in that case, we're looking at ice turning into water, liquid water. All right, we would still use the latent heat of fusion, say, if we're converting water into ice as well. So it also works in that, just to reiterate that as well. Again, the mass of this ice being converted into water is still going to be 0.2 kilograms. We're converting all of it into water. And the latent heat of fusion for water, is 79.8 kilocalories per kilogram. All right, and so that's just a matter of just multiplying those two together, and I get 15.96 kilocalories for that. I get that, I get that. Doing the same now that we're at Q3. This again is going to be a temperature change, and so we're going to go back to MC delta T. In this case, the specific heat that we're going to need is for water. All right, and the amount of mass is still the same. We're heating it all up. The specific heat of water is 1 kilocalorie per kilogram degrees Celsius. And for us, our temperature change final is 100 degrees Celsius, and our initial is 0 degrees Celsius, which makes it just 100 degrees. And so we multiply that all together, and we get 20.0 kilocalories. Moving on, here we have the heat being added to the system in order to convert liquid water into water vapor at this point here. And so we're going to, again, have a phase transition there, but in this case, this is going to be the latent heat of vaporization. All right, and we're converting all of this, again, mass into steam. So we have 0.2 kilograms of liquid water being converted entirely into steam, which was latent heat of vaporization is quite substantial. It's 539 kilocalories per kilogram. And in that case, that gives me 107.8 kilocalories of heat needed to do that conversion. Last but not least, Q5, which is steam. We have a mass of 2.2 kilograms and we just need the latent heat of steam, or sorry, the specific heat of steam and the temperature difference. And the specific heat of steam is 0.363 kilocalories per kilogram degrees Celsius. Our temperature difference is 130 minus 100 degrees Celsius. And so that gives me 30 degrees times this, and that gives me 2.18 kilocalories for that. All right, and so to find Q total, we just add these all up, and I ultimately get 147.9 kilocalories of total heat needed to convert 0.2 kilograms of ice at negative 20 degrees Celsius into 0.2 kilograms of steam at 130 degrees Celsius. All right, that's how much heat is needed to do that conversion. All right, and if you want to know how many joules that is, you can just convert from kilocalories into calories. So you multiply this by 1,000 to get to calories, and then you multiply by the 4.137, I think it is, some number that is equivalent to 1 calorie and however many joules that would be, and then you multiply it by that, and that should give you the number of joules of total heat added, which should be substantially large. All right, any questions on this problem? Do you guys have an example where a total amount of heat doesn't quite fully convert all of the substance into one from one phase to another? Have you guys done that example before?
No.
No? Would you like for me to do that?
If it's necessary for the exam.
I think everything is necessary for you to get a nice, well understanding of everything. But whether or not you might find it useful is a whole other story. So I don't know. I can't necessarily gauge that for you. I can certainly do that and post something without video explanation, but something that is just on pen and paper for later, if you guys want that. It doesn't sound like anyone really wants that, so I will leave it at that. Are there any other questions for me? I'm actually going to do something really quick. Just give me 1 second. I want to see what I actually posted in last year's test and whether or not I did that. Whether or not I would feel evil enough to do it. No, apparently last year I was not evil, so I will not be evil this year. So you lucked out. You lucked out this year. So, okay. Are there any questions concerning the calorimetry stuff that we discussed yesterday with the questions that I had or the problems that I presented to you guys today? Okay. It's sneaking up on that 11:50 time. I don't know if any of you have to leave, but if you do, that's fine. I will continue on with an example of a heat engine, and that will be the final example that I'll give, and then I'll open it up back up to any sort of last minute questions that you might have. Okay, so for the last example, we're on example 4. And this will be an example of a heat engine. Engine, not engineer. I don't know why my brain is doing that. Heat engine. Great. All right. So with these problems, you'll typically be given a pressure volume graph. And in this particular example here, I have the pressures given 4.0 times 10 to the 5 pascals. And actually, I'm going to leave this one blank. I'm going to call this pressure 2. And here I'm going to give the volumes of 0.02 cubic meters. And we might increase the volume or decrease from 0.025 cubic meters. All right, and so we have a point here, and our point there. And this I'll call A. This I'll call point B, and this I'll call point C. And our heat engine is going to have this look here. All right, and the direction of the process will go clockwise like this. So I may ask, what is the net work done by the system if the process connecting C to A is an isotherm? Okay, and then the implication is that these should be straight lines, and so then this would imply that this is a, what would you call this? What would this process be? Anyone have an idea of what sort of process that would be that would connect A to B? Anyone have a guess?
Isobaric, maybe?
It is isobaric. All right. Again, isobaric meaning constant pressure because the pressure at A and B are the same. This implies that this is an isobaric process. What would someone say to the process that connects B to C? What would you describe that as?
Isovolumetric.
Yep, isovolumetric or isochoric, just to be a bit more succinct in writing that. So I needed to make one more adjustment. I needed to just state the number of moles of gas in the system is 2.5 moles. Yeah, 2.5 moles. All right. So again, we're finding what the work, and again, that's going to be the area under this curve. And we defined that this was an isothermal process or isothermic. All right. So what we would need to do is we would need to find the work being done in each of those processes. So we'll first start with A to B. We defined it as an isobaric process, which means that the work from A to B should just simply be the constant pressure times the volume difference. All right. And in this case, the pressure is given as 4.0 times 10 to the 5 pascals. And all we would need is the volume difference. So it's 0.025 cubic meters minus 0.020 cubic meters. All right. And then that gives me 2,000 joules of work being done in that particular process. Now, if we look at B to C, what is the work that's done from B to C?
Would it be the volume times the change in pressure?
Not quite. Remember that the work is the area under the curve, and for a straight line that goes straight up, what would be the area under that? It's still defined as this.
Zero?
It's 0. So for, again, an isochoric process or an isovolumetric process, it's going to be 0 joules of work being done. The next one is now C to A. And so we need to find the work that is done from C to A. And we said that in this process, this process has a specific relationship, and that relationship was the work is equal to N times R times T times the natural log of VF over VI. Give me a second. All right. So with this relationship, we have the initial and final volumes. We have the number of moles of the gas inside our engine that's going through the cyclical process. The only thing that we need to understand is what is the temperature. All right. How could we find the temperature? What do we know about the system? Let's ask this. What do we know about this process? What's the first thing that we know about this process?
It's isothermal.
It's isothermal, which means that the process doesn't change the internal energy and the temperature stays the same. So what we can figure out is what that temperature is at A or at C, because the temperature at A and C should be equal. All right. All right. And we're given information at A and at C. All right, based on the type of process that we're defining here. All right, so at C, we don't have as much information. We're not left with the pressure, but we are given the volume. But at A, we know the volume and the pressure. How are the pressure and volume related to the temperature, say for an ideal gas? What can we use to find that temperature?
PV equals nRT.
Yep, the ideal gas law. All right, and so we can find the temperature, say at A, being equal to the pressure at A times the volume at A over N times R. All right, so we can actually plug this in here. And in fact, we don't actually need this quantity here to calculate the work, because if we plug that in, all right, these constants cancel out, or the ideal gas constant cancels out, and the number of moles also cancels out. And here, our volume final is going to be the volume at A, so we can call it volume A, and then the volume initial is going to be the volume at C, so we can call that volume C. All right, and so we can make a reduction in this equation here by canceling those and seeing that we get, for this particular instance, PA VA times ln of VA times divided by VC. All right. If one were to also ask in this process, what is the temperature of this isotherm, you would then just need to calculate this out as well. So if you wanted to calculate this out for yourself, it's just a matter of plugging in the information. It should be 4 times 10 to the 5 pascals times the volume, which is 0.02 cubic meters, divided by 2.5 moles times 8.31 times 10. Or no, there's no times 10. It's just that. I'm always thinking these constants have more digits than they do. So joules per mole Kelvin. Okay. And let me just doubly verify that this number does come out, because I did it for the other one with a different number, but I just want to make sure. 10 to the 5 times 0.02 divided by 0.5 divided by 8.31. Oh, that's interesting. Okay, I get a different number than that. Let me just doubly verify. Okay, that's fine. I didn't define that number anyways. So this should be 385 Kelvin. Okay, so that's the temperature at point A, which would mean that the temperature at point C is also 385 Kelvin. So one could, in fact, determine the pressure at 2 based on, again, based there we go. So we can find the pressure that is defined at this line here at point C by, again, using the ideal gas law and using this number that we found here with the volume at that particular location. We can determine that as well. All right, but continuing back with the work that we're trying to calculate from the process of C to A, we determine that we can reduce this equation, at least for this instance, in this fashion. And so if we plug that information in, we have the pressure at A being 4 times 10 to the 5 pascals times the volume of 0.02 cubic meters times the natural log of volume A, 0.02 cubic meters divided by 0.025 cubic meters. All right, and so if we continue with that calculation, let me just verify this yet again, because sometimes working these heat engines on the fly can oftentimes create disastrous results. So, all right, which gave me a different number, obviously, because I had a different temperature. But in this case, I get the work that's done is minus 1785 joules. Okay, and so we had this work, and this work being done. All right, and so to find work total, this should just be A to B plus B to C plus C back to A. All right, and so it's just 2,000 joules minus plus 0 plus a minus 1785 joules, which gives me 215 joules. as the total amount of work being done. Okay, any questions on that? Does anybody need any extra time with this, I should say? Okay. Also, I'll make a note here. If we talked about the internal energy of a cyclic process being 0, this implies that the heat gained or lost is minus the work. And so this implies that Q is equal to minus 215 joules. So there is heat being, heat has to be added into this system in order for the net heat has to be added into this system in order for the process to occur. Now note that this is the net heat and not the heat from the hot reservoir. All right, it's just the temperature difference. This would be effectively heat that is converted into work itself. Right, and whatever the whatever the Q difference is, or the Q difference should be this, but whatever the Q hot and Q cold are is based on sort of other questions, or can be answered in various ways, probably from this heat engine itself, based on sort of the initial state that we're looking at here. I can't remember. Let me see here if that can be done. Yes, it can actually. What one can do is, I think one can do it. At least one can potentially get it. That's what you can do. You can find what the internal energy at A and B are via temperatures, since you know, again, the pressures and the volumes at A and B, so you can find what the internal energy difference between A and B is. Since it's an isobaric process, you know the relationship between the internal energy and the amount of heat. And so in that case, that would be the heat that comes in. That would be from the hot reservoir. And then this would be from the heat leaving. This isothermic process would be the heat leaving the system itself, or at least in some of these processes. In other processes here where the total heat can be found going into the cold reservoir. And therefore, hopefully, ultimately, we get a difference between the hot reservoir and the cold reservoir as this, and maybe we can make a determination on the efficiency of this particular heat engine itself. Okay. Any questions associated with this problem here? Does anyone have any other questions for me? Okay. So I think with the practice test, I think the practice test goes into a bit more questions related to sort of a heat engine. So I would kind of look at that as well and go through the solutions of that and kind of understand those, because more than likely you will see a question like that on the test. Though, as I've been keeping these limited to about an hour, um, obviously it's going to be, much shorter in the end. So, but I want to make sure that everything is, covered to the best that I can for these tests. So, all right. If you guys don't have any immediate questions for me anymore with the QA session, I can pretty much call it done if you want it to be done. Otherwise, I'll try and answer any questions you have right now. Otherwise, you can leave. And then I'll see you guys tomorrow.